Okay, this is question 4 from the second part of lesson 5. Always get a question about this one every year, just because it's tricky to wrap your head around. So we have, in this case, a river, and I've already drawn my river. It's 2 kilometers wide, and it flows at 6 kilometers an hour. So we know the velocity of the river is 6 kilometers per hour going downstream. And we know that a motorboat can go at 20 kilometers an hour, so that's the velocity of the motorboat. So I'm going to put VC for current, and the velocity of the boat is going to be perpendicular, because it says it's going perpendicular to the bank, and it's going at 20 kilometers an hour. Oops. So, the question wants us to find the following. Wants us to find how far downstream from the marina will the boat reach the other bank. So this is the tricky part to remember. When you're in the boat, if I'm starting with my boat right here, taking off, and I'm driving straight across, perpendicular, as I move my boat, the current is moving me sideways, and if I really didn't have a reference point to stare at on the other side, I wouldn't even know this is happening, because when you're relative frame of reference, you think you are going perpendicular straight across. However, there is a current vector that's pushing you downstream. So this is a case where vectors might actually clarify the motion of the boat, because if you look at it, the boat simply went from point A to point B, but when you look at it in terms of going across the river, it did go 2 kilometers across. All right, we're not asking how far the boat traveled. We're saying the boat went across the river, and if it went across the river, it went 2 kilometers across. So if we look at it in terms of vectors, in terms of velocity, we know VB, velocity of our boat, equals, and I'm going to set up a standard Cartesian plane. All right, so I'm going to say north. It's heading across the river. So the boat has no east-west component because they're pointing perpendicular to the boat. They're heading straight across, plus 20J, because that's its velocity. It's heading north at 20 kilometers an hour. If we then look at the current, velocity of our current, it has a east component, so we'll say 6I, but the current is not flowing north or south, so it is 0. So our resultant here is the relative motion of the boat. So the relative motion of the boat is 6I plus 20J. So this is a bird's eye view. So if we were flying over top of this boat, this is the direction we would see the boat going. So as a bird, I would see the boat going on an angle. All right. If I am in the current with the boat, so let's say I'm floating in the water. So here's me floating in the current. I'm also moving with the current. So what I see the boat going straight across. And if I'm standing on the shore watching this boat, to me it looks like the boat's going downstream sideways. So those are your different perspectives here. So you kind of got to break it apart and figure out, well, what perspective or what component are we really looking at? So this one is our east-west motion. This is our north-south motion. So all this is preamble to answering the actual question itself. So A, how far downstream from the marina will the boat reach the other side of the bank? Well, all we're wondering is, how far east did it travel? That's all that question is asking. So how far east? Well, all we need then is our east-west component. All we need is that 6I, and we just do our D equals VT. So we want to know how far downstream, if the stream carried it at 6 meters per second, but I'm missing a time. So it's kind of a two-part question, and this, unfortunately, this is the second part. So the first part is how long did it take the boat to cross the river? Well, again, d equals vt because it's not accelerating. We know the river is 2 kilometers wide. If it's traveling at 20 kilometers an hour, we can find our time. So we find that 2 over 20, 1/10, or 0.1 of an hour. Remember, we're working in hours here, so it seems like not a lot, but it actually is 10 minutes, right? Or actually, that's not true, 6 minutes. But so t is 0.1 of an hour. So I can take that up here and plug it in. So I get 0.6 kilometers. They end up 0.6 kilometers east. Okay. So how long will it take? Well, this boat ride ends when you reach the other side, and we've already figured this out. So technically we found B first. So therefore it's 0.1 hour for the trip. All right. Again, this question works because the boat is traveling perpendicular to that stream. So all the components are separate. You can analyze them separately. If the question had some kind of east-west component going with the river, so instead, we would still have our velocity of current equal to 6 kilometers an hour. So when I do my vector addition here, I still have 6i plus 0j, no north or south. But if my boat starts off at any angle other than perpendicular, it's either going to be subtracting from the east-west component or adding to the east-west component. So our velocity of boat is still going to be 20 kilometers an hour cos theta I plus 20 sine theta j. So in this case, that angle right here will determine whether we will be adding or taking away from the current. Then that changes the question a little bit in terms of whether we are, in terms of our time, then we have to do a totally different calculation. Because in this case, we're adding to the 6 kilometers. Our x component is making us travel faster than 6 and faster than 20. If we're going upstream, that velocity of boat in the x, sorry, velocity in the boat in the x. In this case, we're subtracting from the 6 kilometers an hour. So anytime you move off the perpendicular, it will change the question. But for what was asked there, it's realizing that if the boat is simply moving north-south, it does not affect or influence how your river, how far downriver you travel, because it's solely the river's velocity that will determine that. Hopefully that clears that up a little bit. If you have any further questions, let me know.